So, from calculators that filled entire rooms to supercomputer that fit in your pocket, the journey of the central processing unit is one of the most remarkable stories in innovation. And today we are diving deep into how CPUs work, their incredible revolution, and the technology that power every device or you use. So I'm Shania Dries Villanueva, by the way, and let's start with the basics. So what exactly is CPU and how does it work? At its core, a CPU operates on binary data, the bits. A bit represents two possible states, 0 or 1, on or off, and even true or false. So when we combine 8 bits together, we get a byte. Let me draw this for you. So this is a bit. It could also be 0. Bit means only like 1. But when we say byte, we could get this is a byte. It is byte is 8 bits. Byte is 8 bits, yeah. And a byte is actually capable of representing 256 different values from 0 to 255. So multiple bytes form what we call word. The word's size, whether it's a 32-bit or a 64-bit, forms the foundation of a processor's architecture. The Intel 400, the first commercial CPU from 1971, operated on just 4-bit words. So every CPU operates on a continuous 3-step loop: the fetch, decode, and execute. First, fetch. So the CPU retrieves an instruction from memory. Think of think of the CPU as existing in an information bubble. So it pulls data from RAM, processes it, uh, and returns a result. So data travels on what we call buses. The address bus tells the RAM which location to access, while the data bus carries the actual data. This literally look like highways on a circuit board. Second, decode. The instruction is broken down into two parts: the opcode, which tells the CPU what operation to perform, and the operand, which provides the data or memory address to work with. Third, the last is the execute, the CPU's arithmetic logic unit, or the ALU, where it performs the actual operation, whether that's addition, subtraction, or logical comparison. So the result goes to either a register or back to memory. Synchronizing all of this is the CPU clock, measured in hertz. The Intel 400 ran at 740 kilohertz, while modern CPUs nearly 5 gigahertz. That's 5 billion pulses per second. Imagine. On March 1971, Intel releases the 400, a chip with 2,300 transistors that would change everything, compared to ENIAC, built just 25 years earlier. The 400 was 1,800% faster, consumed 99.99% less power, and cost 99.9999% less. The ENIAC weighed 27 tons, consumed 180 kilowatts and cost $5.5 million in today's money. The 404, the 4004, less than an inch long, 1 watt of power, and $5 to produce. This wasn't an improvement, it was actually a revolution. But the real breakthrough wasn't just miniaturization or uh, the decreasing the size, miniaturization. It was what the 4004 represented, a general purpose instruction processing machine. You could program anything inside, and inside the CPU used register the tiny, ultra fast memory location acting as notepad for operation. So the program counter register kept track of which instruction to execute next, incrementing with which step, and branching instruction gave CPU's decision making power. So if a condition is true, jump to this address. If a condition is false, continue here. This simple mechanism is the foundation of all programming logic. And then there's the stack. So imagine a spring loaded tray dispenser at a cafeteria. Data gets pushed onto the top and popped off the top. Last in, first out. So when a program calls a subroutine, a reusable block of code, the return address gets pushed onto the stack. And when the subroutine finishes, it pops that address and returns control. Mess this up, push the wrong button of data, and you get a stack overflow. The program crashes. So by the mid 1970s, CPU design was advancing rapidly. In 1974, Intel launched the 8080, the first true progenitor of modern desktop processors. So the 8080 could run at 3.1 megahertz, had 16-bit address capacity allowing 64 kilobytes of RAM, and while it was an 8-bit processor, it could perform limited 16-bit operation. The 8080 introduced an external bus controller, letting the CPU communicate with slower memory and peripherals without bottlenecking its own operation. So, this chip became the foundation for early desktop computing. In fact, two teenagers in Washington state used 8080 to build a traffic analysis computer for the highway department. Their company was called Traf-O Data, and their names Bill Gates and Paul Allen. So a few years later, they'd found Microsoft, but the real game changer came on June 8th of 1978, the Intel 8086 or 8086. This chip gave rise to what we call the uh, x86 or the x86 architecture, the same architecture powering most computers today. Nearly 50 years later, 50 years, the 8086 was revolutionary. It was a fully 16-bit CPU with 20-bit addressing, meaning it could access up to 1 megabyte of RAM, an enormous amount for that era. It could run up to 10 megahertz, and it featured 8 general purpose 16-bit register with 4 of them capable of splitting into dual 8-bit registers for flexibility. Its segmented memory system was peculiar but clever. With 20 bits of addressing in a 16-bit system, Intel created a windowing system 4 simultaneous 64 kilobyte segments, one for executable code, one for data, one for the stack, and an extra multi-purpose segment. So if you ever run on DOS.com file in the late 80s or 90s, you were literally executing a binary dump of memory segment. The entire program fit in that 64 kilobyte window. The 8060 also cemented Intel's commitment to CISC, or the CISC. CISC stands for Complex Instruction Set Computing. So unlike RISC processor, which use simple primitive instruction executed in one clock cycle, CISC processor have robust instruction sets with complex operation built into the hardware. So for example, early RISC processor lacked multiplication instruction. You had to perform multiplication addition in software to, you have to perform multiple addition in software to multiply two numbers. So imagine that if you have to, it's easy for 2 times 2, but if you're multiplying a bigger number, it is super hassle to add each value. So for CISC, one instruction, it multiplies. So this reduced memory usage and the number of memory access critical when RAM cost over $50,000 per megabyte. CISC also offered orthogonal instruction sets, meaning instruction could operate on any register or memory address with no limitation. No need to shuffle data around them, specific registers, just perform operation directly. The 8086 could even be paired with 8087 floating point uh, cop- coprocessor, which handled complex decimal math operation. Integer math is easy for CPUs, just binary addition and subtraction, but decimal numbers with fraction that normally required slow software algorithms. The 8087 moved this into hardware, performing the 50,000 floating point operation per second. It operates independently, intercepting its own instruction from the bus and processing them while the main CPU worked on other tasks. And then came August 12th of 1981. IBM IBM released the sorry for that personal computer, the IBM PC, powered by the 8088, a variant of 8086. Over 40,000 units were ordered on announcement day. Within a year, it actually had 100,000 sold. So it surpassed the Apple II as best-selling personal computer. The PC era had begun. Microsoft won the contract to develop PC DOS for this machine, or PC DOS. That operating system became their first major product and directly performed then into one of the largest companies on earth. On earth, not just in a specific country, but on earth. So the success of the IBM PC created an entire industry of compatible machines, establishing the PC standard that still dominates personal computing today. Now, let's talk about one of the most important mechanism in computing, interrupts. So this technology introduced in processors like 8008 became the foundation for modern operating system. An interrupt allows hardware signals or CPU events to pause program execution and jump to high priority code. Think of it as emergency override button. For example, you move your mouse. The hardware signals the CPU, stop what you're doing. Run this code now. Okay, so the CPU save its current position, executes mouse handling code, updating cursor position and click status, then return to what it was doing before. All of this happens in microseconds. Microseconds, not even a second, but a microsecond. So the location of interrupt handling code is stored in the interrupt vector table. This is a table in memory where each entry contains the address of code to run for a specific interrupt. So when interrupt number 5 fires, the CPU looks at entry 5 in the table and jumps to that address. So if it fires 5, it looks the CPU at 5 in the table and jumps to that address. So here's it gets fascinating. The interrupt code doesn't have to return control to the same program. It can switch to a completely different program. This is a foundation of multitasking. Your operating system uses a timer interrupt that fires thousands of times per second. Each time it fires, the OS detects to switch a different program. For example, give program A some time to run, then switch to program B, then switch to program C, then back to A. It happens so fast it feels like all programs are running simultaneously, but they're actually taking turns. Another crucial advancement was the indirect addressing. So instead of an instruction pointing directly to data, it points to a memory location that contains a pointer to the actual data location. Imagine you have five five stored in 5 sentences stored in memory at different location. You want to randomly pick one. You generate a random number between 1 and 5, but how do you translate that to the actual memory? Create a vector table with 5 entries, each containing the address of sentence. Now, you can use your random number to look up the correct address in the table. This indirection is incredibly powerful for dynamic programming. Interrupts became essential for device drivers, the code that allows keyboards, hardwares, mice, network cards, and graphic cards to communicate with your CPU. So modern operating systems are built entirely on this interrupt-driven architecture. Every key you press, every mouse movement, every network packet triggers interrupt handling code. So by the mid 1980s, software was exploding complexity. Microsoft Word 1.0 for DOS in 1983, the entire package was just 150 kilobytes with the core executable being only 17,742 bytes. Compared it to the modern Microsoft, which requires 4 gigabytes of disk space and 2 gigabytes of RAM just to start. That's over 200,000 times larger. This software boom demanded more money, more processing power, and crucially, a more a move. I mean, to 32-bit architecture. In 1984, Motorola released the 68020, a true bit 32-bit processor running from 12 to 33 megahertz. It featured 32-bit internal and external data buses, 32 32-bit address buses, and native 32-bit ALU capable of powering 32-bit math in a single clock cycle. This signal count was so high that it required denser pin grid array packaging. You've probably seen this. They're the chips with hundreds of pins sticking out at the bottom in a grid pattern. So the 68020 was used in the Apple, how do you pronounce this one? Apple Macintosh. Macintosh, I guess. Macintosh 2. So the Commodore Amiga uh, 1200 and Sun workstation. So it was a powerful processor, but it still required an internal memory management unit chip. But the Intel's answers was even more impressive. The 8386 or the 80386 launched in 1985 with full production beginning in mid 1986. So the 386 was a revolutionary milestone. It was a true 32-bit architecture running at up to 40 megahertz. It contained over 250,000 transistors. It could address 4.2 gigabytes of memory, absolutely mind blowing for the era when most computers had 640 kilobytes. Imagine the difference of that. And critically, it maintained backward compatibility with previous Intel processor all the way back to 8086. How? By extending the general purpose register to 32-bit while keeping their lower halves accessible at 16-bit registers. And the same instruction set could target both 32-bit and 16-bit operations. So the 386 memory management unit was one of the most sophisticated at this time. It could run in three different modes: real mode, protected mode, and the virtual 8086 mode. So, real mode is 16-bit legacy mode used by DOS and early system. The protected mode, the 32-bit mode with advanced memory protection and segmentation, and the virtual 8086 mode, which allowed multiple DOS programs to run simultaneously in protected bubbles, each thinking it had the whole computer to itself. But the most important feature was the flat memory model. It protected mode with paging enabled. This allowed programs to be loaded anywhere in the memory, in fragments, without knowing their actual physical location. The operating system managed everything through page lookup tables. These formed the basis of modern operating system like Windows, NT, Linux, and Mac OS. Programs could be isolated from each other, protected from crashes, and memory could be efficiently managed. And Intel's even released a budget version, the 386SX, with a 16-bit external data bus instead of 32 bits. This reduced motherboard cost for budget system. The full version was rebranded as 386DX. So, too much words. So, now let's talk about pipelining. Uh, Pipelining, one of the most important performance innovation in CPU history. So, in traditional CPU design, there's a fundamental inefficiency. During the fetch phase, the decode and the execute section of the CPU sit idle, going nothing. During decode, fetch and execute are idle. During execute, fetch and decode are idle. Two-thirds of your CPU is wasting time at any given moment. So pipelining solves this by dividing instruction into sequential stages assigned to different uh, processors units. While one instruction is being executed, another is decoded, and third is being fetched. It's like it's like assembly line. Imagine a car factory. Station one installs the engine. Station two installs the door. Station three paints the car. So without pipelining, you'd build one complete car before starting the next. With pipelining, while Station 1 installs the car engine in a car A, Station 2 is installing doors in a car B, and Station 3 is painting car C. Three cars being worked simultaneously. So this allows much higher throughput and better utilization of CPU's circuitry. It also allows higher clock speed because each pipeline stage is simpler and can complete faster. And the RISC processor with their simple one-cycle instruction are especially well suited to pipelining. Modern RIC processor can have pipelines 10, 15, and even 20 stages deep, but pipelining introduces problem called hazards, data hazards. So data hazards occur when one instruction needs data from instructions still being processed in the pipeline. So imagine instruction A calculates a value and store it in a register. Instruction B, which is right behind it in the pipeline and needs that value. But instruction A hasn't finished yet. So the pipeline must stall, pause, and wait. Performance penalty. Solution include pipeline bubbling, inserting empty stages to create delays, or operand forwarding, passing data directly through the pipeline before it's even stored in registers, or out of order execution, the running independent instruction that don't have dependencies during the stall. And then control hazard happened with conditional branches. A branch instruction says, if this condition is true, jump to this address X. Otherwise, continue. But while that branch is being evaluated in the pipeline, the next several instructions are already being loaded. So if the branch was taken, all those instructions are wrong. The entire pipeline must be flushed and reloaded, and huge performance penalty. So the solution is branch prediction. The CPU guesses which path a conditional branch will take. So modern processor track statistics on branch behavior and use sophisticated algorithms to predict with over 95% accuracy. So when the prediction is correct, no pipeline flush needed. When it's wrong, penalty paid. Software can help too by structuring code so branches are predictable. For example, error handling is usually not taken. So compilers arrange conditional branches to favor a common path. Some advanced processor even use super scalar pipelining, running multiple pipeline in parallel. When a branch occurs, both paths execute simultaneously on different pipelines. When the condition resolved, the wrong pipeline is discarded. No flush needed, but requires duplicate hardware. And early pipelining implementation were simple. The Motorola 68020 used a three-stage decoding pipeline. The Intel 8 the Intel 386 used a loosely coupled three-stage pseudo pipeline where each state was a state machine taking multiple clock cycles. Modern processors, they have pipelines 15 to 20 stages, deep with incredibly sophisticated hazard detection and solution hardware. But pipelining wasn't the only bottleneck. There was another critical problem: memory access. In the early days, accessing memory was only slightly slower than accessing a CPU register. No big deal, but the CPU got faster and faster. Memory technology couldn't keep pace. And by 1980s, a CPU might run at 40 megahertz while memory ran at 8 megahertz. The CPU would sit idle waiting for memory, and huge bottleneck. So using faster memory throughout the system wasn't economically viable. It was incredibly expensive. The solution? Caching. A cache is a small amount of ultra fast static RAM placed between the CPU and main memory. It acts as the buffer, storing copies of frequently accessed data. When the CPU requests data, it first checks the cache. And if the data is there, a cache hit, it's retrieved instantly. If it's not there, a cache miss. It must be fetched from slow main memory and a copy is stored in the cache for future use. So on modern processor, a cache hit might one clock cycle. A cache miss to main memory might take 200 to 300 clock cycle. So during that time, hundreds of instructions could have been executed. Cache performance is critical. So cache design exploits to two principles of program behavior: the spatial locality. So if you access a memory location at X, you'll likely soon access location X plus 1, X plus 2, and so on. So data near each other tends to be used together. Second is the temporal locality. So if you access memory location X, you likely access it again soon. Recently used data is likely to be reused. So caches are organized into cache lines or blocks, chunks of memory, typically 64 bytes in modern processor. So when you request 1 byte, the entire cache lining contained it is loaded. Now, how do we organize cache? So there are three approaches. First, direct mapping, the simplest. So each memory address maps to exactly one specific cache line. Fast to check, but creates conflict. If two frequently used memory address map to the same cache line, they keep um, evicting each other, trashing. Second, fully associative, the opposite extreme. Any memory address can go in any cache line. No conflict, maximum flexibility. But to find data, you must search entire cache. Slow and complex. Third is the set associative, the practical compromise. Compromise. So the cache is divided into sets. So each memory address maps to exactly one set, but can go in any cache line within that set. So modern processor typically use two-way, four-way, eight-way, or 16-way set associative caches. So excellent balance of speed, flexibility, and complexity. So when a cache set is full and new data arrives, which existing line gets replaced. This is the placement policy. The most common is least recently used, or the LRU. So the cache line that was accessed longest ago gets evicted. So the logic, if it hasn't been used recently, it probably won't be needed soon. So writing data creates another complication. When you modify data in the cache and the main memory are now out of sync. Two approaches: write through Uh, write through is where every write to cache is immediately written to main memory. Simple but slow and generates lots of memory traffic. Second is write back. Modified cache lines are marked dirty and only written to main memory when they're evicted from the cache. So, much more efficient. And in multiprocessor system or systems with DMA, direct memory access, where devices write to memory independently of the CPU, you need cache coherence protocols to keep all the cache synchronized. So, early cache implementation were tiny. The Motorola 68020 had just 256 bytes of instruction cache, but the Intel 386 had no internal cache at all. But motherboards could add up to 64 kilobytes of external cache. By 1990s, caches evolved into multi-megabyte hierarchical system. So modern processors have L1 cache, tiny but ultra fast, split into separate instruction and data cache, typically 32 to 64 kilobytes per core. The L2 cache, larger and slightly slower, typically 256 kilobytes to 1 megabyte per core. The L3 core, the L3 cache, even larger, shared among all cores, typically 8 to 64 megabytes. So some high-end processor have L4 cache, cache hit rates on well code on and can exceed 99%. That means only one in 100 memory accesses hits slow main memory. And that is why cache is absolutely critical to modern CPU performance. Now, let's briefly discuss the CPU's specialized cousin, the GPU or the graphics processing unit. While CPUs are designed for complex sequential tasks with lots of branching and decision making, GPUs are built for massive parallelism. So a CPU today might have 8, 16, or 32 cores. A modern GPU has thousands of simple cores. Uh, and NVIDIA RTX 4090, for example, has 16 cores. CPUs have complex control logic, large caches, and sophisticated branches prediction. So each core can run different program independently. GPUs have simple cores with minimal control, logic, and small caches, but they can run the same instruction on thousands of pieces of data simultaneously. This is called SMID architecture, single instruction, multiple data. GPUs were originally, I mean, originally designed for rendering graphics to display a 1920 by 1080 image at 60 frames per second. You need to calculate the color of 1124 million pixels per second. So each pixel calculation is independent, making it perfectly parallel. But this parallelism is useful for more than graphics. GPUs now power artificial intelligence. Training neural networks involve massive matrix multiplication, perfectly suited for GPU parallelism. Scientific computing, weather simulation, molecular dynamics, physics simulation, even cryptocurrency mining, calculating hashes in parallel. Uh, Also, video encoding, processing each frames independently. Training a large AI model on CPU might take months. Yeah, it actually take a lot of time and patience also. So on GPU cluster, days or even hours. This parallel processing revolution enabled the deep learning boom of the 2010s and 2020s. So the trade-off is that GPU are terrible at sequential tasks with lots of branching. The Excel, when you have a simple operation repeated millions of times in different data to bring all this concept together. That's example the SAP one, simple as possible computer version 1. It's a teaching tool that demonstrates fundamental CPU principle in the simplest way possible. So SAP 1 is an 8-bit computer with just 16 bytes of RAM. It has 5 instructions. The first LDA, load accumulator. Copy data from a memory register into the accumulator register. Second, the add. Add the value from memory address to the accumulator. Third, subtract the value from the memory address from the accumulator. Fourth, out. Display the accumulator content on an output display. And fifth, HLT or halt execution. Stop the program. That's it. 5 instructions. But with these 5 instructions, you can write meaningfully programs. The architecture includes program counter, hold the address of the next instruction, and memory address register, hold the address being accessed. 16 bytes of RAM stored both programs instruction and data. Instruction register holds the current instruction being executed. Controller sequencer decodes instruction and control operation. Accumulator, the main register for arithmetic operation. ALU performs addition and subtraction. B register holds the second operand for ALU operation. Output register display result. So here's a simple program. Let's add 5 plus 3. So if we add 5 plus 3, address 0, LDA 14, load the value from address 14 into the accumulator. Address 1, add 15, add the value from the address 15 to the accumulator. Add 2, address 2, out, out, or it displays the result. And address 3, HLT, HLT, it stops. And address 14, 5 minus the number 5, 5, the number 5, and address 15, 3, the number 3. The program counter starts at 0. So it fetches the LDA instruction, decodes it, and execute it by loading the value 5 from address 14 into the accumulator. Counter increments to 1, fetches add instruction, decode it, execute by adding 3 from address 15 to the accumulator. Accumulator now contains 8. Counter increments to 2, fetches out instruction, decodes it, execute by displaying 8 on the output. Counter increments to 3, fetches a HLT instruction, program stops. So this simple computer demonstrates every fundamental principle we've discussed: the fetch, decode, execute cycle, registers, memory access, the ALU, and the program sequencing. From this simple design, we can trace a direct evolutionary line to billions of transistors in modern processors. The principle remained identical, just scaled to incredibly complexity with pipelining, caching, branching, prediction, and parallel execution. That's it. And now, let's recap this incredible journey. So, from 2,300 transistors of Intel 4004 in 1971 to the 50 billion transistor in modern processor like an Apple M2 Ultra, from 740 kilohertz to 5 gigahertz clock speed, from 46,000 instruction per second to over 1 trillion instruction per second, from 16 bytes of addressable memory to 16 exabytes. This exponential growth enabled everything we take for granted today: smartphones with more computing power than 1980s, supercomputer, artificial intelligence that can understand and generate human language, the internet connecting billions of devices, medical imaging that saves lives, autonomous vehicles, space exploration, and scientific breakthroughs. Every photo you take, every message you send, every video you watch, every game you play runs on this principle. The fetch, decode, execute cycle. Registers, the ALU, memory management, pipelining, caching, and we're not done. The next revolution is already beginning. Quantum computing that operates on qubits instead of bits, neuro more the neuromorphic processor that mimic brain architecture, photonic chips that use the light instead of electricity, 3D stack processor, and the chiplets that combine different technologies. The evolution of processing power is the evolution of human potential. Every advancement opened new possibilities that previous generation couldn't even imagine. And the next chapters, we're writing it right now. Thank you for joining me on this journey through the evolution of the CPU processing power. I hope you've gained a deeper appreciation for the incredible engineering that powers our digital world. Thank you. Bye.